What is tensile test? A tensile test is a standard, cost-effective method in material science used to pull a material specimen from both ends until it breaks. By applying this controlled pulling force, researchers and engineers can continuously monitor how the material behaves under stress. The test maps out a material journey from initial loading to total failure, usually visualized as a stress-strain curve. This profile simultaneously measures two critical properties, which is mechanical strength and ductility. Mechanical strength is how much load the material can handle, and ductility is how much the material can stretch. A key takeaway from this measurement is the ultimate tensile strength, the absolute peak stress a material can withstand before it begins to narrow and ultimately breaks.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Dinesh Aizal bin Abdul Malik with metric number AD250176. This slide shows the result of the specimen measurement before and after testing for aluminium and mild steel shaft. Before testing, the average diameter of the aluminium specimen was 8.00 mm, while the mild steel specimen had an average diameter of 8.31 mm. For the length measurement, aluminium had an average length of 88.17 mm and mild steel had an average length of 88.61 mm. However, after the testing, we can see significant changes in both materials. The average diameter of aluminium decreased from 8 mm to 5.69 mm, while mild steel decreased from 8.31 mm to 5.41 mm. For the length, aluminium increased from 88.17 mm to 100.1 mm, and mild steel increased from 88.61 mm to 64.01 mm. For the conclusion, this result indicates that both specimens experienced diameter reduction and length elongation after testing. Comparing the two materials, aluminium showed a greater increase in length, suggesting that it is more ductile than mild steel under the applied load. Therefore, the testing confirms that both materials underwent plastic deformation, with aluminium exhibiting higher ductility. That's it from me. Thank you.
So, hi everyone. First we have setup and inspection. The metal sample is wide at the ends of gripping and narrow in the middle where stretching happens. Before starting, we record this initial measurement with a caliper. When pulling begins, it enters elastic phase and the data curve goes into a straight line, and this stretching is only temporary. If we stop, it snaps back into its original shape. If we keep pulling it and it will move into a plastic stretching, which is the curved band, and the material suffer permanent and an flexible damage. Next, the pulling force hits its absolute highest peak, known as ultimate strength. Past this peak, the middle of the sample visibly narrows down and called as necking, and finally it snaps thinly into two pieces. And that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faris Ikhwan bin Fazli. My number matrix DD250041. So this is a calculation for lab tensile. So you can see the aluminium and mild steel have a initial diameter, initial gauge length, final diameter and final gauge length. And firstly, you can calculate the Young modulus. So you can calculate Young modulus aluminium, and you can get the stress and strain. And also you calculate the mild steel too, and you can get the stress and strain. After you can get both of aluminium and mild steel, you can also calculate Young modulus elongation for steel and mild steels. And lastly, you can calculate the percentage reduction of area. So the percentage reduction of area evaluate the material structural deformation capacity up to the fracture. And you can see the aluminium for percentage is 49 and mild steel you can get the 55%.
My name is Muhammad Khairani Lukman bin Muhammad Khairul Anam, with my number metric is AD250157. So moving on into a discussion section, we begin with question A, which compares the mechanical properties of mild steel and aluminium. First, look at the stiffness through Young modulus. Mild steel is roughly 3 times stiffer than aluminium, measuring at approximately 200 gigapascal compared to 70 gigapascal. This meant that under the exact same load, mild steel will experience significantly less bending and deflection. Second, regarding yield strength, mild steel has a distinct, much higher yield point. It handles a larger amount of stress before it permanently deforms or loses its original shapes. Finally, mild steel achieves a much higher ultimate tensile strength. It can carry a significantly heavier maximum load onto the stress strain curve before it begins to neck and break. Now, for question B, we evaluate the identification and direct impact of three primary experimental errors. The first is load cell error, caused by a faulty sensor calibration or electronic drift in the universal testing machine. This incorrectly shifts the recorded force data up or down, introducing a systematic mechanical error across the entire stress axis. Next is cross-sectional dimension error, which occurs from inaccurate manual measurement using the vernier caliper. A minor error here directly skews the initial cross-sectional area calculation. Lastly, gauge length measurement error happens due to improper marking or misreading of the gauge points. This invalidates elongation tracking, directly distorting the calculated strain data and skewing the slope used to find Young's modulus. Now, we conclude with question C, looking at the international standards required for testing different classes of materials. For metals, testing governed by standards like STM E8 or ISO 6892. Plastics are tested under STM D638 or ISO 527, where they are pulled slower because they are stretched differently. Ceramics follow STM C1273 or C1161, which utilize bending configurations instead of pulling because ceramics are highly brittle. These standards are critical for three major reasons. First, they ensure reproducibility, giving engineer accurate data so bridges, buildings, and car don't collapse. And finally, they provide reliable quality control, allowing factories to prove their materials meet the bio-exact requirement. That's all from me.
The tensile test successfully evaluated how the material behaves under a pulling force, revealing two distinct stages of stretching. In the initial elastic phase, the material stretched temporarily and predictably, allowing us to calculate its stiffness, known as Young's modulus. As the pulling continued past this limit, the material entered a plastic phase, meaning it was permanently deformed until it hit its absolute peak load, which marked its ultimate tensile strength. After reaching this peak strength, the sample narrowed down at its weakest point and snapped, providing engineers with the exact safety and reliability limits needed to use this material safely in real-world structures.